Okay, now I'm pleased to welcome our speaker, Justin Cooper. Justin is a principal software engineer at Rolls-Royce based in Birmingham, UK. And since 2018, he's been working with Rolls-Royce and the University of York, developing domain-specific languages, model-based tooling, and model transformations.
Thank you very much, Samuel. So, hi everyone. Thank you for coming today, and thank you to Abeo for inviting me. I'm Justin Cooper, and I'm leading the development of CaMCOA Studio, which is Rolls-Royce's modeling workbench for deploying engine control software. So, CaMCOA Studio has been under development for approximately the last 4 years, and today I'm going to give you an introduction into what CaMCOA is and how to create a minimal deployment using CaMCOA Studio. I'll also cover our experiences of developing CaMCOA Studio. So firstly, I'll give you a little bit of background into the project. So Rolls-Royce Control Systems supplies engine control and monitoring systems for applications such as civil aerospace. With each new generation of engine, the systems and software that needs to be produced are massively increasing in complexity. And as such, Rolls-Royce Control Systems want to focus on model-driven engineering. As many of you will already know, model-driven engineering provides several benefits, such as being able to simulate, validate, and test at early stages of development. It offers more of an accessible syntax for engineers to develop algorithms in, and it provides opportunities to auto-generate code and automate processes. So a key component of switching to a model-driven approach is a new software architecture that Rolls-Royce must adopt. This architecture, known as CaMCOA, is a component-oriented architecture which provides a standardized platform to base all new control and monitoring systems on. This architecture supports the development of applications in Simulink, as well as auto-generating all of the code for deploying these Simulink services on different hardware platforms. So we'll be exploring CaMCOA Studio, which is our workbench for deploying instances of the CaMCOA architecture. So this is the CaMCOA architecture, and over the next few slides, I'll talk through each of the different components. Here you can see the split between application software and the operating system, as well as what parts of the architecture can be generated by each tool or whether they're hand-coded. So at the bottom, we have the microcontroller abstraction layer, which abstracts all of the details from the underlying hardware to provide a common interface to the platform layer and the node abstraction layer, and this is hand-coded. So we next have the platform layer, which provides common operating system functions, such as scheduling facilities, networking facilities, and memory management. Again, this is hand-coded. Then we have the node abstraction layer, which allows for the controlling of actuators and converts the low-level microcontroller data from the microcontroller to engineering units. For example, a low-level analog to digital value from an analog to digital converter needs to be converted to a temperature unit for an application to be aware of the temperature of the component in the engine. All of this logic is modeled in Simulink. However, any of the deployment-specific data, such as read and write addresses, is modeled in CaMCOA Studio. CaMCOA Studio can then instance a Simulink model, providing the full driver implementation by doing a model-to-model transformation. Next, we have the configuration layer, which defines all the code required to start, set up, and schedule the system. This layer is modeled within CaMCOA Studio, and all of the code is automatically generated using the Epsilon generation language, EGL. The data distribution layer is responsible for passing data between the application layer, the platform layer, and the node abstraction layer, and also inter-application communication. Again, this is modeled in CaMCOA Studio and automatically generated using the Epsilon generation language. Finally, we have the application layer. This is modeled in Simulink and is responsible for the actual controlling and monitoring of the system. An example of an application may be to start the engine. This requires application to communicate with the hardware via the data distribution layer, the node abstraction layer, and finally the microcontroller abstraction layer. So now you've seen the architecture, I think we should work through a hello world introduction within CaMCOA Studio. So basically the simplest deployment possible. Here we'll create two Simulink services. One service will produce some data, the other will consume the data. These services will be running on two different hardware platforms, and the producer will send data to the consumer via Ethernet. So firstly, we'll create a very, very simple Simulink service, which we'll call test out. And this is going to produce some data. We've just got some constant blocks going into an adder. So if you were to ever simulate this service, it would always return the result of 2. And it's going to send that result to an output. We'll also create another application to actually receive this data or consume this data. And we'll call this test in. Here, we're just reading from the port and we're stubbing the data. We're not going to do anything additional with the data. So now we've implemented our application services, we can go into CaMCOA Studio. Here we can define the hardware platform we want the application to service to run on. In this example, we're going to run one of those services on a PC node. This PC has two comms interfaces. One's a UART and one's a network interface, and we'll be running Ethernet via this network interface. As you can see, this is all modeled using EMF and Sirius. So we've got a Sirius diagram here with palette tools for a user to construct a hardware platform. Next, we define another hardware platform. This time, we're going to use a COTS processor, the TMS570. Again, just for simplicity, this will just have two network interfaces, one for UART and another for Ethernet. So now we can import our Simulink models into CaMCOA Studio because we've got a hardware platform to run those models on. CaMCOA Studio provides an importer application which can be invoked by a context menu, and this will transform the Simulink model into a CaMCOA representation of the Simulink model via a model-to-model transformation. This is implemented using the Epsilon's transformation language ETL. As you can see, CaMCOA doesn't need to be aware of the internals of the service. All it needs to be aware of are the inputs, outputs, any data types, and the step functions that Simulink provides. Basically, the step functions are what Simulink allows the execution of the service to happen within. One challenge is keeping the CaMCOA representation of the Simulink model in sync with the actual Simulink model. During our model validation stage, we check whether the two models are actually in sync and they actually match. If there's a mismatch between the services, we raise a validation error and then offer the user an Eclipse quick fix to actually resolve the mismatch. And what we do is we leverage the EMF compare framework to provide that differencing and merging interface. So here you can see an example where a data type has changed between the actual Simulink model and the CaMCOA representation of the Simulink model. On the left-hand side of that EMF compare window, you have a type of Boolean for the output 1. On the right-hand side, you have the CaMCOA representation of the service, which is saying that the output is of type uint32. What we do is we offer the ability to replace what's in the CaMCOA model with what the Simulink model actually is via the EMF compare window and all the tools provided there. It's impossible to merge the other way. Next, we need to allocate our services to the target hardware, and we do this by allocating appropriate RTOS tasks. So as you can see there, under priorities 3 to 9 of the PC software, we're going to run the test in service, and on priorities 3 to 9 of the TMS570 software, we're going to run the test output service. That period is defined by Simulink, and it's defined in the Simulink model. That's something that we imported when we imported the application into CaMCOA Studio. And the rest of the tasks deal with the networking side of processing the message. So A664 task there is dealing with the A664 driver, which is a specific implementation of Ethernet. And also in the platform, you've got the processing of messages dealt with PCNet and TMS 31net. So all we need to do now is we need to allocate the flow of data between the two services. So here we need to be able to send data from test out to another system. So again, we have another Sirius diagram which enables you to do that. And we've got some tools which allow you to click on the data to say that the data is going out to a different system. You can also send it to a different channel if it was a dual channel architecture, or to another service if we had multiple services running on that particular node. Next, we need to enable the data to be inputted into the PC. So again, we use the palette tool within Sirius to actually say that the data for the input signal is coming from another system. So we've also got the ability to customize the initial value of data being sent. And we can do this by using an Xtext DSL, which is a C-like DSL that we've written to actually allow you to specify what the initial values of any data of the services actually are. So this is embedded within the Sirius properties view, and it supports features like content assist, error markers, and syntax highlighting. So now we've said that the data needs to be sent from the TMS 570 to the PC, we now need to actually make that connection at the top level. So we're saying that out1 is directly connected to the input on the PC software. Once we've established that link, we can then allocate that data to be sent on a message. And once it's within a message, we can then allocate it to a physical network link. So here we've drawn an Ethernet link between the two network interfaces on the hardware platforms. So the data is going from the TMS 570 to the PC on network interface 1. And we've allocated our data to be sent on that physical link there. So that's it. We can then use build targets within CaMCOA Studio. This will generate all of the deployment code from the CaMCOA model, as well as invoking the Simulink code generator. This will then give you a binary which can be uploaded to the target platform. So without even writing a line of code, you can send data between two Simulink services via Ethernet on two different hardware platforms. And that's the key of CaMCOA Studio. We're automating that entire deployment process. So a user can send data, can define a hardware platform, and write their services in Simulink without worrying about writing any of the glue code for deploying all of that. All of those resources, and also generate the binary files to then run on the target hardware. So just a few quick notes on the size and scale of CaMCOA Studio. We've seen just a very simple deployment of a couple of application services on the target hardware, but in reality we're obviously modeling much more complicated systems. We've got a fairly complicated meta model, and realistically, CaMCOA deployments contain at least 3,000 model elements. We've got many tables, diagrams, model constraints, and model transformations transforming to all different sorts of models, mainly to, we're transforming to C code, but we're also transforming to different model types, like Simulink, and then using Simulink's code generator. So this image isn't supposed to be too readable, but it's just supposed to give you more of an idea of what diagrams look like in a more representative CaMCOA deployment. So now I want to quickly talk you through the underpinning frameworks of CaMCOA Studio. So CaMCOA Studio is built on top of a variety of different frameworks, and over the coming slides, I'll cover each one, and I'll note the experiences that we've found with each of these frameworks. So firstly, we've used the Eclipse Modelling Framework for creating the abstract syntax of CaMCOA Studio. We chose this because of the great modelling ecosystem available with EMF. So for example, there's so many great frameworks like Sirius, which allow you to build concrete syntaxes on your eCore meta, based on your eCore meta model. There's also some great tooling to be able to define eCore models as well. So we firstly started off with eCore tools. However, as our meta model became more complicated, we're having issues ensuring that our diagrams are readable. So we switched over to emphatic, which is a textual syntax for eCore. And then we generate graphical views of our meta model using Picto, which is a tool part of the Epsilon family of tools, which allows you to create static views of models via model-to-text transformations. eCore is a well-established language, and there's lots of good documentation out there and a lot of great examples. However, one of the challenges that we faced is when we're going to make changes to the meta model. You can quite easily break models when you change the meta model because all of the existing models conform to the old meta model. So to work around that issue, we've been using the Flock tool, which again is part of the Epsilon family of tools. Flock allows a mapping between two different meta models to be written, allowing for the automation of model migrations. Here you can see a snippet of the migration taken from the Epsilon support article, where the concept of a port has been changed in the meta model to be a domain concept of an import and a concept of an outport. Basically, port was too generic, and they've needed to change port into be an import and to be an outport. So as you can see, the script will automatically migrate any model conforming to the original meta model into the new meta model. So this allows you to write logic to create or modify the model elements during the migration. And we found that very useful while we were evolving our meta model. So we've made substantial use of the Sirius framework for creating our diagrams. We really like the interpreted nature of Sirius, which gives us rapid feedback on changes. There's some really great work on integrating Sirius with the Eclipse layouting framework, and we've seen some really positive results in auto layouting our diagrams. So even though Sirius is interpreted, we've not really had any performance issues with diagrams. So we've got diagrams containing over 100 model elements, and there's no real lag in that. One of the things that we have found quite challenging is testing and reviewing the viewpoint specification model, so the O-design model. We've tried a couple of frameworks, RCPTT and SWTbot. Both of these frameworks are GUI testing frameworks that actually click and drag and drop and modify the model elements using the same tools a user would. Both have their advantages and disadvantages, but we've felt that we've been more successful with SWTbot because there are a lot of examples within the Sirius GitHub repository, and we've managed to get some good GUI tests working. However, it's still quite a laborious process to actually write these GUI tests because there's no support from basically a tool to actually record actions. We found that this wasn't supported on Sirius diagrams. We've also had some really positive experiences with Xtext. It's been really easy to define DSLs using the grammar language. It's been really customizable, provides a lot of entry points to customize, like the syntax highlighting, the content assist. And basically, because it's EMF based as well, we've had great success with integrating like Xtext and Sirius together. So we're able to access like the abstract syntax as a abstract syntax tree as an EMF model, and this has allowed us to have references between like the Sirius-based DSL and the Xtext-based DSLs. It's very easy to test. There's great testing frameworks, testing support based on JUnit, and the only downside is obviously it's not interpreted, so you must regenerate all the changes as necessary, basically. So there's no quick feedback like there is with the Sirius framework. So the Epsilon framework is a family of tools which supports model management activities such as code generation, model validation, and model transformations. We found it really useful to have dedicated model management languages such as ETL, the model-to-model transformation, which is the model-to-model transformation language, and EGL as well, which is the model-to-text transformation language. Epsilon supports many different modeling types, so you can write, you have support for the Eclipse Modelling Framework, Simulink, XML via the Epsilon connectivity layer, which means you can access and perform model management activities on many different model types using the same language and same family of tools. That's something that we've struggled with in the past because we've needed to have very low-level knowledge of the MATLAB API to be able to create, or sorry, the Simulink API to be able to create model elements. The Epsilon model connectivity layer abstracts all of that information away, so you can just focus on the task of actually just creating that mapping between the source and target model in the model-to-model transformations. So ultimately, this has helped us quickly generate artifacts from our models, and we also get the trace information on how the generated artifacts actually relate to the model. One of the minor challenges that we've had is the developer support mechanisms in Epsilon could be improved. So, for example, code completion, debug facilities, etc. It's not been sometimes the easiest thing to debug during model transformations, and actually navigating around large scripts you don't get the same editor support as you would for like developing Java applications, for example. So I briefly want to talk about some of the more general challenges that we've encountered whilst developing CaMCOA Studio. So one of the things, obviously, is there's many engineers working on CaMCOA models. Parallel working with file-based models has been difficult. We use Git as our version control tooling with Azure DevOps interface. EMF Compare has been our preferred framework for model comparison and merging. However, our engineers have not really found this a trivial tool to use. EMF Compare is very good if you're working with trees or have familiar with the underlying meta model. However, a lot of our users are typically editing the model using a Sirius diagram or Sirius table. So when they start to see the tree structure of the model, it can become confusing because they're not familiar in modeling using the tree editor. They're used to modeling using like the diagram editors. Engineers have noted that conflict resolution in EMF Compare can also be very confusing. So what we did is we tried to use the EMF Compare Sirius integration. However, engineers also got confused because then that takes into account the diagram elements as well as the actual semantic elements. And knowing what to do when you're merging diagram elements is also found quite confusing to the engineers. So they tend to then just resort back to just the plain comparison of the semantic model rather than dealing with any of the diagram representations. So there's quite a lot more work for us to do to investigate more of the advanced features of EMF Compare, such as the filtering, and actually try and improve the user experience. But in the shorter term, we've just found by splitting the CaMCOA deployments into as many different files as possible, or what makes sense to split into a different file, is significantly reducing the number of conflicts. Because it's something else to note that if you're using Git as your version control system, if you have a conflict on the file level, it might not necessarily be a conflict in the modeling level. EMF Compare is very good at picking that up, saying there's no conflicts with the model. But if you're relying on Git just to do your merging, you can get pseudo merge conflicts actually in the model. So model reviewing is another issue that we're facing. So we use pull requests to review work before actually accepting that work onto a master branch, and this typically happens within the web browser. So, like for example, if you're doing a pull request in GitHub or Azure DevOps, for example, the comparison tooling only supports text-based comparison. And this makes identifying some of the changes very challenging. So when you're looking at non-human readable IDs like you are there, that outputs reference there without looking through the entire file to find where that ID was defined, you can't tell, for example, what element has actually been removed very easily at all. So this results in the reviewer checking out the model in Eclipse and then having to switch to the web browser and then add the comments in the web browser, trying to find the correct location in the file, and then having to switch between the model in Eclipse and then having to add the review comments within a web browser is quite a laborious, error-prone task. And ideally, we need to be able to understand all the changes within the web browser. We also had the issue that it's sometimes difficult for new users to understand what diagrams should be used to complete certain tasks. The thing is, when you've got a domain-specific language, it's really great for domain experts because they can get to grips with the domain very quickly because they're familiar with it. But somebody new to the company might find a domain-specific language quite confusing, especially when the domain is very complicated and there's no there's no easy resources to go out there and Google a specific problem in the domain-specific tool. So we've tried to make this a little bit easier by implementing a custom workflow UI, which basically guides users around the tool, shows what diagrams are available at a certain point, allows you to open and create diagrams, etc., and navigate to certain wiki pages. So we've had mixed feedback relating to the workflow. Some find it hinders their performance because the diagram button or step that they want to find is buried under several other steps within the workflow. Also, because this is an entire custom implementation as well, there's been a few bugs, and it's not been a great way to onboard a user, we found in general, into the software deployment process within CaMCOA Studio. So instead, we're going to investigate like the Capella activity style navigation, which is a lot more lightweight, and hopefully just being able to provide lightweight documentation, all the listed diagrams available on specific viewpoints will improve the user experience for experienced users, but also be accessible enough for new people using the tool. Something else we found genuinely difficult is actually developing and deploying Eclipse-based applications within the Rolls-Royce network. And if anybody was embarking on the journey tomorrow, I'd seriously recommend getting an internal package manager repository set up within the corporate network, and this managed by the IT department. We've had lots of issues where, because we don't have centralized repositories of all the libraries, everybody ensuring that we're using the same version, showing that we can update everything, we can scan things for license and security issues. By having a centralized repository, it certainly makes the management of building a Eclipse-based application a lot easier. But also actually deploying like CaMCOA Studio, so Eclipse-based applications, hasn't been an easy task either. We've experimented with deploying via Eclipse update sites and or pre-building zipped distributions and oomph as well. And all of these have their advantages and disadvantages, but none of them have actually provided an easy deployment process or a great user experience. Something that's had to be quite hard to actually implement, and basically it's very difficult to get everybody using the correct version of the tool, having to take time to download pre-built distributions, etc. So deploying Eclipse-based applications has been quite a difficult task for the adoption of CaMCOA Studio. So in summary, we've successfully implemented a domain-specific modeling workbench based on the Eclipse Modelling Framework and all the technologies, and that is transforming the way that engine control systems are being deployed within Rolls-Royce. So this is also enabling Rolls-Royce to transform the development and deployment processes of engine control and monitoring systems to model-based approaches, and by interfacing Simulink and auto-generating all of the software deployment, we are massively reducing the deployment times from months to now days where you can define a deployment of an engine control system. A few challenges still remain, but we're looking at adopting some of the latest cloud-based modeling technologies. For example, could Sirius Web help us with the parallel working and the model reviewing, seeing as everything's in the web browser? And that's something that we just started investigating. So, and also just a final note, we're certainly not at the end of our journey with domain-specific modeling at Rolls-Royce. So far, we're approaching the end of CaMCOA Studio version 1. However, in version 2, we're looking to extend our modeling capability into systems and electronics. We're looking to model new platforms and applications and provide a better, more collaborative user experience through web-based applications. We're always interested to learn and hear and contribute to the community. So we want to keep this communication line open. And yeah, thank you so much for listening to the presentation. And I'd like to invite any questions.
Yeah, thanks, Justin, for your presentation and for your insights. It's quite interesting. Well, we have a few questions, but I'm sure we will have much more. And probably also, well, maybe if you advise, considering the list of questions and open points you have. Yes, you haven't mentioned the effort required to develop your environment. Okay, can we have a few figures about it? Yeah.
Sure. So CaMCOA Studio has been under development for the past 4 years. We've had approximately 3 to 4 engineers working on CaMCOA Studio full time. CaMCOA Studio is part of the wider CaMCOA project. So you could see from earlier on in the presentation, we have like the platform layer and also the null layer, so that they're not directly part, and the MCAL layer, they're not directly part of CaMCOA Studio. There's hand-coded processes within there. So the entire CaMCOA team is about 15 people and developing over 4 to 6 years.
Okay, thanks. That, and well, you displayed a diagram, but maybe we have a question about that. Yes. Yeah, exactly. We have this one. So what is let's say the complexity of your models?
So yeah, I guess it really depends on what engine. The absolute minimum is 3,000 model elements, but we've been up to probably about 9,000 model elements. So yeah, 9,000 is probably the biggest CaMCOA model that we've created.
You answered this one already.
So in terms of users, there's up to 40 people using CaMCOA Studio, and they're all internal within Rolls-Royce at the moment. Well, obviously, when we hope to adopt maybe a web-based modeling platform, we could offer that to different areas of the business or different businesses. And how many projects? So we've got 2 projects using it at the moment for actual engine development, and we've got 5 or 6 in the pipeline coming up.
Okay, if this is for an engine, is the autocode generation qualified?
So the qualification process, so a lot of the application development is auto-generated by Simulink. So that provides the Simulink qualified tooling. The autocode qualification within CaMCOA Studio, so that's still a little bit of work in progress as we come to actually put these and put the software generated by CaMCOA Studio actually onto engines.
Yeah, this one is interesting. Would it make sense to share your studio with others?
Definitely think there is scope for having CaMCOA Studio as a open source project in its most basic form. For example, just being able to write applications in Simulink and being able to automatically get all the glue code required to deploy it on different hardware platforms, I think is very powerful. So I think in the most basic form, I would push to maybe to make CaMCOA Studio an open source project, and then obviously you'd have the qualification and that side of stuff as being more commercial.
Well, this question is mine, but my interest other people. So you mentioned what you call parallel working, and I'm just wondering, is a Obeo designer team might be an option for this need?
So we tend to use, well, as far as I'm aware, Obeo Designer is database backed, I think, which does that then have mechanisms such as locking and releasing specific parts of the model. So we are very much using the file-based version control systems. So I guess what you could have is a collaborative element using Obeo team, and then once the collaboration session has kind of ended with the user, you could possibly download the model in its file form and then put it in our version control system, and then at least that would enable some sort of like Google Doc style collaboration with engineers.
How much time is required to train an engineer on the studio?
So that's a good question, and it's a difficult one to answer because people who've been working in the domain for 20 years are very familiar with the domain concepts, but maybe take some time to actually pick up what diagrams should certain things happen in, and that sort of familiarity. So that's very quick for somebody to learn. But there's also, well, if I had to say, you could pick that up in a few days. But training an engineer to work on CaMCOA Studio who doesn't really have that much knowledge in the domain, probably talking a few, at least a month to actually understand what the domain is and how everything kind of relates to it.
Okay. And this means that there is a new role, which is a CaMCO trainer or something like that.
Sorry, what was the cut?
No, I'm just wondering if, due to the time required to learn CaMCOA Studio, is there a new role in your organization with someone dedicated to the training of newcomers?
So we don't have really the capability to do pair programming to try and learn or onboard somebody. I mean, that would be really nice if we had the capability and the number of people to be able to support that. So we've typically been relying on things like wiki pages and a more informal like conversations.
Okay. And next question. Did you try to use your model for simulation and have measurement like worst case execution time?
So we don't simulate the actual CaMCOA model. However, we do integrate tooling such as worst case execution time tooling, which uses the CaMCOA model. So that isn't actually part of CaMCOA Studio, but it utilizes CaMCOA Studio. Thank you very much.
So have a good day and goodbye.